All right, welcome everybody. So let's get started. It's a pleasure to welcome today's speaker. It's Tamar Bar-On from Bar-Ilan University, and she's going to tell us something about profinite completions of free profinite groups.
Okay, thank you very much. I will start with some background, and I not know what considered as a common knowledge in New York, so you can feel free to ask questions or say it's trivial, you can skip it. Okay, so we start by definition of profinite completion. So let G be an abstract group, not topological. The profinite completion of G is a pair of a profinite group. We denote it by G hat, but we need to justify this notation. And then homomorphism I, which satisfies the following universal property. Anytime we have a homomorphism from G to a profinite group H here is profinite, then we can lift it in a unique way to a continuous homomorphism phi hat from G hat to H. Now it's easy to see that if G has a profinite completion, then it's unique. So we can denote it by G hat. And every group has a profinite completion. We have an explicit construction. G hat equals to the inverse limit of all the finite quotients of G, together with the natural epimorphisms between them. Together they create a directed system of finite groups. So it has inverse limit, which is a profinite group. So some examples. The profinite completion of a finite group is the group itself. The profinite completion of the integers is the infinite product of ZP, the p-adic integers, when we run over all the prime numbers. And the profinite completion of Q is 0, since Q has no finite quotients. And some properties, the image of G into its profinite completion is always dense. In addition, the natural homomorphism I from G to G hat is injective if and only if G is residually finite, which means that the intersection of all subgroups of finite index or normal subgroups of finite index, it's the same, it's trivial. Now we move to profinite groups. If G is a profinite group, then by definition, we know that G is isomorphic to the inverse limit of all its finite continuous quotients, which means G modulo U, when U is an open subgroup of G. But G hat is isomorphic to the inverse limit of all the quotients G modulo U, where U is a subgroup of finite index. Now it's known that in a compact group, every open subgroup has finite index, but there might be subgroups of finite index which are not open. So G is not necessarily equal to G hat. We saw that a finite group is always the profinite completion of itself, but it's not necessarily true for every profinite group. And we say that G is strongly complete if G equals to G hat. So as we saw, G is strongly complete if and only if every subgroup of finite index is open. So let's give an example of a profinite group which is not strongly complete. Then we take a finite group H and I an infinite set of indexes. And we define the following group. G equals to the product of copies of H over I. Together with the product topology, G is a profinite group. We need the following definition. For every profinite group, we denote by omega 0 of A. This is the local weight of the profinite group.
By the product, you mean the actual full unrestricted product, right?
I didn't understand.
This is a direct product. This is not a direct sum, right?
Yeah, direct product, not sum.
I see. Okay, thanks.
The direct sum is not a profinite group. The local weight of every profinite group is the cardinality of the set of all open subgroups of A or open and normal subgroups of A. It doesn't matter, it equals. And it is known that the local weight of G of this form equals to the cardinality of I, because every open subgroup is of the form, it's actually an open subgroup of just a finite product of copies of H, when we take a finite subset of I. So now we know how many open subgroups G is. In order to build a subgroup which is not open but has finite index, we need to be familiar with one more thing, filters. A filter F on I is a subset of Pi which satisfies the following properties. It doesn't contain the empty set, it is closed to finite intersections, and it's closed under increasing. If A belongs to F and A is a subset of B, then B belongs to F2. An ultrafilter is a filter which satisfies, in addition, that for every subset of I, either A or A complement belongs to F. So if F is an ultrafilter, then for every finite partition of I, A1 to AN, one of this subset must belong to F. It's easy to prove it. Now, if we take an ultrafilter F on I, we can define the following subgroup, HF, to be the set of all the tuples, HI, such that the set of indexes J, for them Hj equals to E, belongs to F. It is a normal subgroup, and actually G modulo HF is isomorphic to H. And we can see it by taking the fixed tuples. For every element in H, the tuple which is fixed on this element, they are not equal to each other, because the set of indexes for them they are equal is the empty set, which doesn't belong to F. And any element is equal to one of them. Because H is finite, then one of the elements of H must, the set of indexes for them it equals to this element belongs to F. There is one element of H which satisfies this property.
What was capital H here?
What is H?
Yeah, capital H. So
H is the finite subgroup we started with. G is equal to infinite product of copies of H.
Oh, I see. Okay.
Okay, so this is a subgroup of finite index. Okay. And it is known that on an infinite set, there are two power the cardinality of the set, different ultrafilters. And now we saw that for every ultrafilter, we can create a different subgroup. These subgroups are different if F is different. So there are at least, but actually exactly, 2 power the cardinality of I subgroups of finite index, and only cardinality of I open subgroups. So G is not strongly completed, and actually it is many subgroups of finite index which are not open. Most of these subgroups are not open. Okay, so there are profinite groups which are not strongly complete. There is a famous theorem of Segal and Nikolov that every finitely generated profinite group is strongly complete. They are not the only groups which are strongly complete, but almost only. Most of the profinite groups are not strongly complete. And one remark that we need, it's not about the example, a profinite group is always residually finite, so we can think it as a subgroup of G hat. We will need it in a few minutes. Okay. Now we move to free profinite groups. Let X be a profinite space. A free profinite group over X is a profinite group we denote by fx, equipped with a continuous function I from X to fx, which satisfies the universal property that you think any function, continuous function, because X is a profinite space, it is a topological space. So any continuous function from X to a profinite group H can be lifted in a unique way to a continuous homomorphism from fx to H. For every profinite space X, the free profinite group over X exists and it is unique. So we can denote it by fx. If X is a finite set, we can consider X as a profinite space with the discrete topology, and then any map is continuous. So it is a pretty easy observation that the free profinite group over X is actually the profinite completion of the abstract free group over X. If we want to generalize this to an infinite set, things become a bit more complicated, because if we consider X as a topological space with the discrete topology, we want most of the maps to be continuous. X is not profinite space anymore. So what we can do, we want to close it to be a profinite space, and we do it by the one-point compactification. The one-point compactification of X, it's true for every topological space, but here is the definition only for a discrete space, is a space when we add one more element to X, and we call it Esterize. With the following topology, the open subset are the subsets of X and the cofinite subsets that contains Esterize. And this is not just a topological space, this is a pointed space. Every profinite group can also be considered as a pointed space by taking the identity element E to be the distinguished point. So obviously we talk about pointed maps. So Esterize is like the identity element. Notice that a function from the one-point compactification of X to a profinite group H is continuous if and only if the reduced function from X to H is what we call converging to 1, which means that every open subgroup of H contains almost all the elements of fx. So we don't need to think about the one-point compactification with this element. We can just talk about X with maps which are converging to 1, and we want to extend such maps. Okay. Let X be an infinite set of cardinality M. The free profinite group over the one-point compactification of X is called the free profinite group over the set X converging to 1 and denoted as Fm. M is the cardinality. And X is called a basis for Fm. In particular, X is a subset converging to 1 of Fm, because the map from X to Fx needs to be continuous, and in our case, it means converging to 1. Some properties of free profinite groups. The local weight of Fm, M here will always denote an infinite cardinality, equals to M. If G is a profinite group with local weight M, then G is a quotient of Fm. And actually, every free profinite group, so it's a mistake, over some profinite space is either finitely generated, and then it is isomorphic to Fn when n is the number of generators, or it's isomorphic to some Fm where m is the local weight of G. So if we want to talk about free profinite groups which are not finitely generated, it's enough to talk about the profinite groups over sets which are converging to 1. And this is all the free profinite groups we have. One way to determine whether a profinite group is free is by embedding problems. It's called embedding problem, but here you see a projection, and the reason is that it comes from Galois topology, and there is an embedding of the fields. So an embedding problem is diagram as follows: G projects over C, B projects over C, A is the kernel. A solution to the embedding problem is an epimorphism from G to B, which makes this diagram commutative. If G is a profinite group of local weight M finite, then G is free of rank M if and only if every embedding problem where B is finite has exactly M different solutions. And actually, it's enough to take such embedding problems where A is a minimal normal non-trivial subgroup of A. So first notice that Fm is not strongly complete, and we can see it by looking at the projection on the infinite product of C2 over cardinality M, Z modulo 2Z. As we said, Fm projects over every profinite group of local weight M. And we know that this group is 2 power M subgroups of finite index. So their pre-images are subgroups of finite index of Fm, but it has only M open subgroups. So free profinite group, which is not finitely generated, is not strongly complete. And actually, the local weight of its profinite completion is equal to 2 power M. And our main question is whether the profinite completion of Fm is a free profinite group of rank 2 power M. So first of all, notice that if X is a set converging X, the basis of Fm is not a set converging to 1 in Fm at. We said that we can consider G as a subset of G at, so Fm is a subgroup of Fm at, and that's X2. So the basis, any basis for Fm is not a set converging to 1 in Fm at, so it cannot be extended to a basis of Fm at. Okay, we still didn't say what's the answer for this question, but we would accept that if Fm at is also a free group, then we can take the basis of Fm and extend it to a basis for Fm at, and it can't be done. And why is that? Okay. Fm, let Fm be a free profinite group over the basis X, and we look at the group G, which is the product of copies of Z modulo 2Z or C2 over the naturals. And we define a map from X to G by the following. We choose a countable subset of X. We denote it by Y, it equals to the set of Y1, Y2, and so on. And we define Fy1 goes to 1, 1, 1, so on. Fy2 goes to 0, and then only 1. Fy3 goes to 0, 0, and then 1, and you get it. And all the rest of the elements goes to the 0 element. This is a converging to 1 map. You can see that any open subgroup contains almost all the elements because it contains all the elements from one level and then on. And it goes on to a set of generators. This set generates the group G, generates topology. So it induces an epimorphism, phi from Fm to G. Now, if we take an ultrafilter F on N, we can define the subgroup HF, as we did in the beginning. This is the subgroup of all types, such that I will remind all the types such that the set of indexes for them it equals to 0 in this case belongs to F. So you can see that all these elements. Okay, sorry, I didn't say it, but we need to take an ultrafilter which contains all the cofinite subsets. It's not a problem. And then all these elements doesn't belong to HF. So phi minus 1 of HF is a subgroup of finite index that differs from X by infinitely many elements. And thus, this is not a set converging to 1, because in Fm at the profinite completion, the subgroup of finite index of Fm becomes an open subgroup. So there is an open subgroup such that the difference between M and X is not finite. Okay. Fm at is free of rank 2 power 2 power m if and only if the following property is satisfied. Any finite embedding problem of abstract groups of the following form, where A is a minimal normal subgroup, has 2 power 2 power m abstract solutions. Okay. Abstract embedding problem, it means that the maps are not necessarily continuous, so phi is not necessarily continuous. We want that in this case, there will be 2 power 2 power m, not necessarily continuous, epimorphisms psi I from Fm to B, which makes the diagram commutative. Okay, Fm is free, so we know that if phi is continuous, there are m continuous epimorphisms. Now we want that for any epimorphism phi, there will be 2 power 2 power m epimorphisms. Why it's equivalent? We will show only one direction, the one that show that if this property is satisfied, then Fm at will be a free profinite group. So in order to prove that Fm at is free, we need to show that every embedding problem, now embedding problem of profinite groups when phi is continuous, is 2 power 2 power m continuous solutions. So we look at an embedding problem. B is finite, A is minimal normal. We can compose phi with the natural homomorphism I from Fm to Fm at. There is a natural homomorphism from every group to its profinite completion. The composition now is not continuous because I is not continuous. Okay. This is still not an embedding problem from Fm because we don't know that the composition is an epimorphism. But it's true. The image of Fm is dense in its profinite completion. We said it. So since phi is continuous, the image of I of Fm under a continuous function is dense in C. But C is finite, so it has the discrete topology, and the only dense subset in a discrete space are the subset are the set itself. So the image of I, Fm under phi is C. So the composition of I and phi is an epimorphism, and thus we get an embedding problem from Fm, an abstract embedding problem. Okay, by assumption, it is 2 power 2 power m abstract solutions, which means epimorphisms from Fm to B, which makes this diagram commutative. Okay, by the universal property of the profinite completion, every epimorphism can be lifted to a continuous epimorphism from Fm at to B. So now we get 2 power 2 power m continuous epimorphisms from Fm at to B. It's not enough. We need to say that this diagram now is commutative with psi I at, alpha, and phi. And why this is true? Because we know that psi I at, if we compose it with I, it's equals to psi I. So we get that phi and the composition of psi I at and alpha identify on the image I of Fm. And this is a dense subset. C is discrete. We saw it. So it's Hausdorff. So we get two continuous functions from a topological space to an Hausdorff space, which identify on a dense subset. So they are actually equal. It's a known fact in topology. So in order to prove that the profinite completion of Fm is free itself, we actually need to solve abstract embedding problems for Fm by enough ways. Unfortunately, I don't know to do it, but I know to do it in a very specific case. So I'm sorry to disappoint you. Wait till the end, there will be surprises. Okay, so our partial results is the following. An embedding problem for Fm where phi is continuous is 2 power 2 power m abstract solutions. Okay, so again, what it's known since Fm is free, it's that there are m continuous epimorphisms from Fm to B, which makes diagram commutative. And what we are going to show is that in addition, there are 2 power 2 power m not continuous epimorphisms from Fm to B, which makes diagram commutative. Proof. We denote by U the kernel of phi. This is an open subgroup of Fm because phi is continuous. So U, it's a profinite group itself. We know that there are m continuous solutions, psi I from Fm to B, and we denote by Hi the kernels of psi I. So for all I, Hi is an open normal subgroup of Fm, and it is a subgroup of U. Okay, since A is minimal normal, and I am not going to prove it here, there is a subset J of I of the same cardinality of I, such that the natural homomorphism from U to the product of U over Hj for every J in J, which is actually isomorphic to product of copies of A, is epimorphism. Since this row is an epimorphism, then for every ultrafilter F on J, we get that rho -1 of AF, the subgroup that F creates on the infinite product of copies of A, as we saw a couple of times today, is a normal subgroup of U with quotient isomorphic to A, because we know that the infinite product of A modulo AF, the subgroup that the ultrafilter creates, is isomorphic to A. sorry. Okay, you can notice that rho minus 1 of AF is also a normal subgroup of FM, because actually we have the following equation. I'm sorry, this map is not necessarily on top. There is a homomorphism from FM to the product of FM modulo this HJ, the same J that we took to make this map an epimorphism. This is not necessarily an epimorphism. We can't promise it. But there is a natural homomorphism, and there is an epimorphism from U to this infinite product. That's the way we choose J. And U is contained in FM, and so U modulo HJ is contained in FM modulo HJ. So this is a commutative diagram, and actually the ultrafilter F creates a subgroup in the product of A and also in the product of B in the same way, by the same definition. So rho minus 1 of AF is equal to the intersection of U with rho prime minus 1 of BF. And thus it is normal in FM. It's a simple computation. We would like to prove that the quotient map from FM to FM modulo rho minus 1 of AF is a solution. And since we know that there are 2 power m ultrafilters, we will get enough solutions. For that, we need to prove that FM modulo rho minus 1 of AF is isomorphic to B. So we will get a homomorphism from FM to B, and immediately by the definition of AF, we will see that this map's commutative. Okay. Then first notice that the cardinality of FM modulo rho minus 1 of AF, obviously it equals to the cardinality of FM modulo U times the cardinality of U modulo rho minus 1 of AF. FM modulo U is isomorphic to C. This is the kernel. And U modulo, this is the group we project on. And U modulo rho minus 1 of AF is isomorphic to A. So the cardinality of FM modulo rho minus 1 of AF equals to the cardinality of B. So this is a good start. In addition, since the natural homomorphism from U to the product of U modulo HJ is onto, there are preimages for the fixed tuples. So there is a set of representatives x1 to xn for all the HJ in U. x1 to xn are set of representatives for every HJ in U. Choose a set of representatives y1 to yt of U in FM. Then the set of products xi, yj is a set of representatives for all the hj in FM. Thus, the images rho prime of xi, yj are different than each other in every component. So they are not equivalent modulo BF. And thus the composition map from FM to the infinite product of copies of B modulo BF is onto. So I will recall again, rho prime is not necessarily onto because we just take a subset J of I to make this map, rho from U to the product of U modulo Hj onto. This map is not necessarily onto, but the map from Fm to the infinite product of B modulo Bf is onto. So Fm modulo rho prime minus 1 of Bf is isomorphic to B. Finally, it's just a computation. The cardinality of B equals to the cardinality of Fm modulo rho minus 1 of AF. This is what we saw in. But rho minus 1 of AF is equal to the intersection of U with rho prime minus 1 of BF. So this group projects on this group, but they both have the same finite cardinality, so they are equal. And thus we get that Fm modulo rho minus 1 of AF is isomorphic to B as we wanted. And since there are 2 power 2 power m ultrafilters, we get 2 power 2 power m abstract solutions. Unfortunately, we made it only for continuous epimorphisms. So there is enough work. Okay, and now for some positive results. We can ask the same question we asked for free groups for projective groups. What is a projective group? Let G be a profinite group. We say that G is projective if every embedding problem of the following form, B and A are profinite groups too, is weakly solvable. Weakly solvable means that there is a homomorphism pi from G to B, which makes diagram commutative. So, okay, I change it to psi. It doesn't have to be an epimorphism. It's just homomorphism. Okay, and it can be proved that it's enough to consider finite embedding problems, which means that B is a finite group and then A must be finite too. So a profinite group is projective if and only if it can solve in a weak way every finite embedding problem. Let G be a profinite group. G is projective if and only if it is isomorphic to a closed subgroup of a free profinite group. Here is the connection between projective groups and free profinite groups. And so we get that every closed subgroup of a profinite projective group is also projective because it is a closed subgroup of a free profinite group. For projective groups, we do know that the profinite completion of G is also projective. Here is not just a conjunction. We have an answer. Okay. By a similar proof to the case of free profinite groups, we can prove the following lemma that let G be a group, a profinite group, then G hat is profinite projective group if and only if any abstract embedding problem of the following form where B and A are finite groups is weakly solvable. So again, in order to prove that the profinite completion of G is projective, we need to show that G can solve here in a weak way abstract embedding problems. So here is the proof of the theorem. We are not going to prove the lemma because it's really the same. So let G be a profinite projective group, and we have a finite embedding problem. Phi is not necessarily continuous. B and A are finite groups. We choose a finite set of preimages of the elements of A, x1 to xn. For every finite subset, not subgroup, just subset of G, we define HY to be the closed subgroup that generates by X and Y. Since X is a subset of HY by definition, then the restricted map phi from HY to A is an epimorphism. Since H is finitely generated, then by Segal and Nikolov theorem, H is strongly complete, which means that every subgroup of finite index is open. So every homomorphism from HY to a finite group is continuous. And thus, phi restricted to HY is a continuous epimorphism. HY is a closed subgroup of a projective group, so it is projective itself. And now we have an embedding problem from HY. There is a continuous epimorphism from HY to A. So there is a weak solution, which means a homomorphism psi y from HY to B, which makes the corresponding diagram commutative. We denote by calligraphic A of Y the set of all continuous weak solutions, which is homomorphisms from HY to B, which makes diagram commutative. Since HY is finitely generated, then HY is finite because there are only finitely many homomorphisms from a finite continuous homomorphisms from a finitely generated profinite group to a finite group. If Y is contained in Z, there is a function from, it should be AY and AZ, which sends every homomorphism to the restriction. Every homomorphism from HZ to HY, we just restrict it. And obviously, if Y is a subset of Y prime, which is a subset of Y prime prime, then the functions are compatible. So we get a directed system of finite sets, the AY and these functions. It is known that a directed system of finite sets always have a non-empty inverse limit. It means there is an element in the inverse limit. An element in the inverse limit is homomorphism F, which goes from the union of all the HY to B, and it satisfies that the composition of alpha and F equals to phi, because it's true for every element. But the union of all the HY is equal to G, because we run over all the finite subset of G. So we have every element here. And thus we get a weak solution to the embedding problem, a homomorphism, which is not necessarily continuous, obviously. This is a inverse limit of continuous maps, but it's not continuous itself. But we get a homomorphism from G to B, which makes the diagram commutative. And that's all. So I finished a bit earlier.
All right. Okay. Thank you very much. So let's thank Tamar for an interesting talk and also for finishing early. Thank you.
So,
Okay.
question?
So if there are any questions to the speaker, now you're welcome to ask.
It's midnight for me, so you really don't have to.
Okay, that's all right. So if there are any questions to the speaker, please go ahead.
I have one question.
Yes.
Yes.
So I think you said something like there are not much more strongly complete profinite sigma groups other than finitely generated profinite groups. So you mean in the sense that it is known some theorem that describes precisely
Yes, actually there is. Some
Okay.
profinite groups which are strongly complete are exactly the groups such that the number of finite index groups is of any index is finite.
Mhm.
So in finitely generated groups, it's obvious that there are only finitely many open subgroups of any index. It's really not trivial that there are finite number of finite index subgroups which are not open, but this is the situation.
Mhm.
So this is a full characterization of all the strongly complete finite groups.
Mhm.
So they need to be very small.
Mhm. Okay.
All right.
Thank you.
Are there any other questions?
Tamar, I looked for a preprint, but I didn't find one.
Yeah.
I work on it.
Okay.
I see.
Hopefully soon.
Okay. Thank you. Thanks for a nice talk. I hope you get some sleep.
Thank you.
Thank you.
Thank you very much for listening.
Okay. All right. Let's thank Tamar again. Thank you. Okay, so now I'll stop the recording. So the official type part will be over.